Hi everyone, it's Mr. Canfield. So today we're going to be looking at average and instantaneous rates of change. I can read. So this is one of the big ideas in calculus, and we're going to start out and just remind you, average rate of change. If you want to find, if you have a curve and you know 2 points on that curve, the average rate of change is literally just the slope between those 2 points. Oh no, I hope the sniffing doesn't sound super loud to you guys. I'm not feeling great, but want to get this video out there. Dedication to that YouTube grind. No. So in our last class we talked about this table here, and I'm just going to show you on screen now how we can get this table really quickly into our calculator. So I'm just going to clear my memory really quick. I forget everything. All right, so we're using f of x is x squared in this. So if I go in and I go y equals, and I go x squared. So I'm going to look at the graph and wow, it's a parabola. I'm so surprised. But if we push second and then we push the graph button again, it brings up the table. The issue is this table, it says we want x values of 2, 1.5, 1.1, 1.05. Not these. So it says press plus for delta table. The problem is that means the change between those. This is not a consistent number. So it's going to be really annoying to change that a whole bunch. Instead, what I'm going to do is I'm going to push second and then window brings us to table setup. And so it says table start. That's the top number here. Sometimes you want to use a different number, but I'm going to leave it at 0. I don't care about that because I'm going to change the independent variable to ask. And now, so I hit enter on that, it highlights it. Now if I push second table, or go in there again, now it's blank. The calculator is politely asking me. It says, Canfield, what do you want? Well, I want x to be 2. And it's oh, okay. And then it does it. I want x to be 1.5. Oh, okay, then it does it. 1.1. Oh, okay, then it does it. 1.05. Okay, and then it does it. 1.0. You get the point. Maybe you don't get the point. I can't read your mind. But here's my table. And now I can just copy those numbers. Saves a good amount of time, especially if we're doing these things by hand, or if we were, it's a lot easier than going 1.01 squared, and then you have to go back in. And now remember, you can push up on the TI-84s and beyond and hit enter, and that sort of thing. This is just a time saver. I highly recommend it. So the idea is we're looking at different slopes between, from if we're looking at this, oh wait, that's not the right graph. We're trying to be okay, so from 1 to 2, we can find what we call a secant line, the slope of the secant line. And so the slope from 1 to 2, well, we know that's 1, that's 4. If we're trying to find the slope, the table is just saying, I'm flipping you off, sorry. The table says, no, this is more comfortable. The table says rise and then run, and then MSEC. This is just saying what's the slope of our secant line. So this is just to kind of help you out if you want the rise. Well, we're going from 1 to 4, so our rise is 3. The run, that's our x change, goes from 1 to 2, and that's a 1. So the rise over run, the slope between 1 and 4 is 3. So we could say the average rate of change, I'm going to zoom in here. I'm going to go from 0 to 2 on my graph, and then I'm just going to, my y values, I'm going to go from 0 to 5. It's saying our average rate of change on this graph from 1 to 2 is 3 over 1. 3 units up per 1 unit over. But what we can do is, if we were to, instead of going from here to here, if we did a slightly smaller window, so to 1.5, let me just pull these numbers off. So if we pull these numbers off, so like instead of going from 1 to 2, if we go from 1 to 1.5, we'll be able to calculate the slope from 1 to 1.5, the average rate of change between those two. And so I don't know if you're noticing this, these numbers get progressively closer and closer and closer and closer to 1. So I'm going to focus on this one. We've got a rise here of 0.002 from 1 to 1.002. And we've got a run of 0.001. So if I do 0.002, oh wait, let me get the typo. Let me get the full number here. So let's take this number divided by 0.001. So did I do something wrong? I definitely did something wrong. Oh. I'm bad. My bad. This is 0.002, and then there's another 001 after it. Sorry. Anyway, come back. So take that number. That's our rise divided by our run. 2.001. Okay, so we started out from 1 to 2. The average rate of change was 3. From 1 to 1.001, the average rate of change was 2.001. Here's the problem, though. At 1. Let's find a secant line at 1. So how far away is 1 from itself? None. So our run is nothing. How much higher up is this y value than it was when it was 1? Nothing. We can't do the slope formula at one point. The slope formula fails. And we're going to need to introduce something new. Oh, sorry. Maybe you don't know why it fails. 0 divided by 0. The universe exploded. All right. We're not allowed to divide by 0. So because of that, we have to develop something new. So before we do that, though, we're going to spend a little bit of time talking about kind of generalizing these secant lines and generalizing tangent lines and stuff like that. So and we talked about this in class last time, but if we have point P and point Q, and we call point P like X and Y, and Q is X and Y, the problem is like X1, Y1, and stuff like that. He's saying P is X sub 0, Y sub 0, and Q is X sub 1, Y sub 1. So our slope formula would be this one minus this one over this one minus this one, right? Y1 minus Y0, X1 minus X0. We are going to use slightly different notation, though. We can use a single variable if we do this right, because this curve is f of x. And so what we can do is we can say, instead of saying y sub 0, we can say f of x sub 0. That might not feel good right now, but this is the notation that we're going to use. So just try to get used to it. You can remind yourself it's the same as y sub 0. This one, f of y sub 1. And so that's what he has. I'm dumb. I meant to say x sub 1. Okay, when I say I'm dumb, I don't actually think, oh, I'm stupid because I wrote that. It's like, oh, I made a mistake. Like, that's all I mean. It's a colloquialism. All right. So when it says the slope of a secant line is just y2 minus y1 over x2 minus x1. He's using slightly different notation, but that's all this is saying. All right. What we're going to do is we're going to keep point P where it is. So this and this they're going to be what they normally are. But we are going to take this and we're going to go, and we're going to get it closer and closer and closer and closer to that point. And so eventually what it's going to look like is this guy over here. We'll talk more about that later. So the thing that I care about right now is us being able to talk about average rates of change and then doing some estimations. So let's say we have f of x is equal to x squared plus 1. we're going to find some stuff, and then we're going to confirm it. So it says, let's find the average rate of change between x equals 1 and x equals 3. So if we do that, I'm going to set it up with my formula first. I'm going to say, well, this is f of my second one minus f of my first one over my second one minus my first one. Right? That's how I'm going to find my average rate of change. And like, if you're the kind of person who likes to do like part A of a whole bunch, you could literally just drop down f of the second one minus f of the first one over. That's our average rate of change every time. In May, when you take the AP exam and it asks you for average rate of change, you can totally use this. Oh yeah, this is on the AP exam. So let's see. This I do expect you to be able to do by hand, so I'm going to do it by hand right now. Let's see. I'm going to say that's 3 squared plus 1 minus 3 squared plus... Oh, wow, yeah. Plug in 3 both times, Canfield. Wait, you don't do that? I made myself laugh. That's the worst. My wife gives me a hard time when I make myself laugh. She thinks it's cute. She's like, I can't believe you made yourself laugh with that. And I'm like, I know what's wrong with me. So, anyway, I get 10 minus 2 over 2. So I got the average rate of change between 1 and 3 is 5. I want to find our estimation of the instantaneous rate of change at x is equal to 2. And the way that I'm going to do that is kind of similar to what we did before. I'm going to plug x squared plus 1 into my calculator. And then on my table, I'm going to use 2, and that means like 2.001. So this isn't perfect, but it's good enough for now. So I'm going to say estimated instantaneous rate of change. So if we do that, our estimated instantaneous rate of change at x equals 2. So from 1 to 3, it's 5. This is like the halfway point, right? So we're going to see how is this related to 5? Is it more than 5, less than 5? Is it close to 5? So if we check it out, I'm going to use f of 2.001 minus f of 2 over 2.001 minus 2. Now, why did I pick 2.0? I just wanted to pick something close. You could have picked something slightly different. We're estimating. Just pick, you're going to use 2, and then you're going to use something really stinking close to it. That's the main idea here. So that's 5.004001. If you're annoyed that I'm saying O's, I should say zeros. I know. So, and then I'm going to plug 2 in. I get 5. On the bottom, I get 0.001. I'm just going to use my calculator real quick. 5.004001 minus 5 divided by 0.001. And I got 4.001. So my estimation is that the instantaneous rate of change at x equals 2, I'm actually guessing it's probably going to be 4, because this is like a little bit off, so it's probably going to be 4. So my estimation is 4. We're not going to do this a whole bunch. We're going to learn how to do this and get the exact number very, very soon. And secret, some of you already know it actually because you took honors calc last year, or you're in physics and your physics teacher told you. Secretly, it's a lot easier than what we're doing. But we kind of have to see where things are coming from before we can do that. So the equation of the tangent line at x equals 2. So I don't want you to use y equals mx plus b. You're allowed to. The thing is, I don't know the y-intercept of the line, but I do know that my estimated slope is 4. So we're going to say that that's m. So I could say y is equal to 4x plus b, and then we can solve for b by plugging in 2, 5, right? Our point's 2, 5. If you're missing how I got 5, we plug 2 into the original equation. So you could do that. Here's my recommendation. Use point slope form. If you haven't learned point slope form before, just off on the side real quick. Remember that m is equal to y2 minus y1 over x2 minus x1. If we multiply both sides by that denominator, we get m times x2 minus x1 is equal to y2 minus y1. You might notice a striking similarity between these two things. The way point slope form works, you leave the y alone, m turns into slope, you leave the x alone, so our slope was 4, and then our point was 2, so x minus 2, point was 5, y minus 5. Guess what? I'm done. I gotta stop there. Students are coming into my room.